Hi, my name is Mr. Warnow. Some of you may know me from my wonderful YouTube series, and some of you guys may know me from being a teacher. But I'm here to tell you something today. We've been talking about derivatives, and many of you are like, Mr. Warnow, I'm not a really big fan of derivatives. Well, today is your lucky day, because today we start talking about antiderivatives, and they have everything we need to be more successful in calculus. So let's go ahead and get started. Let's imagine we're given a function, a derivative, and we're told that the derivative of the function is 3x squared. But we want to find out what the OG, what the original function was. What would you say that derivative would be? So in other words, remember what we're saying is f prime of x equals 3x squared. Well, we know when we take the derivative, we had to originally drop the power and then subtract 1. Well, if we subtracted 1, this was originally a 3, which is this 3 down here that was dropped. So we could say the original function was x cubed, which is what most of us would probably say. But I have other options too. Because we remember, if we take the derivative, when we take the derivative, we have a constant, and that constant just becomes 0. So we really don't know what this constant was originally. So it could have been a 1, so the answer could have been x cubed plus 1. The original function could be x cubed minus 7. It could be, this constant could be anything. If I take the derivative of all three of these functions, I would get 3x squared. So what we tend to do is we tend to make it more generic. So what we'll say is f of x equals the function x cubed plus some constant. Now we're going to call it C1. We'll talk more about that later on. So this constant now becomes more generic for us. Now, f of x is what we call the antiderivative, because we're going the opposite way. Instead of taking the derivative, we are going the opposite. Instead of subtracting our power, bringing our power down, subtracting 1, we're trying to find out what the original function was. So we call it an antiderivative. The symbol, and this symbol right here looks like a big letter S, and well, that's a big hint for us. This symbol right here is what we call an integrand. And what it stands for is that we are taking, is just another word for an integral, which we'll talk about in just a moment. So the symbol, the integrand of g of x dx, you might remember when we did differentials, talked about differentials, we had this little dx right here, is the antiderivative. This is what the symbol means. The antiderivative of g of x with respect to x. Now this g of x dx should look very familiar to you. It's going to be very important for us later on. And an important thing to remember is that g of x is a derivative. So what we're really looking for is we are looking for the original function. Now, the term antiderivative is a synonym for integral. So you're going to hear us say it many different ways. Some people like to say the antiderivative, some people prefer the word integral. They mean the same. We get the word integral, of course, from the symbol, an integrand. So we call it so this whole process is just called an integral. Now, there is a difference between antiderivative and integral, but it's not really a major thing we need to talk about right now. We'll discuss that later on. So we have a few antiderivative rules, and these come from the integration rules come from our derivative rules. So kind of an easy way to remember it is that antiderivatives and derivatives are inverses of each other. So we just go the opposite direction, which we'll talk about in just a second here. So they are inverses. In other words, it's kind of like when you back in 8th grade mathematics, 5th grade mathematics. If I'm adding x plus 3 equals 7, to solve it we use an inverse. So instead of what's the opposite of addition? We subtract 3 from both sides. We subtract, so that's the opposite. They're inverses. And adding and subtracting are inverses. They cancel each other out. The same thing works for integrals or derivatives and antiderivatives. And we can use that to help us find the integration rules. So let's take a look at them real quick. So if we know that the derivative of x to the n, this is our power rule, drop the n and subtract 1, so we n times x to the n minus 1. To do the integration rules, we do the exact opposite. So instead of subtracting 1, we're going to add 1 to our power. And then instead of multiplying by the original power, we're going to divide by the new power. N plus 1. It's the complete opposite. So here we would drop our power and then subtract 1. Remember, we would be multiplying. So here we're going to do the opposite. The inverse of subtraction, we add 1, and then instead of multiplying by the power, we divide by the power. Now the only thing you need to remember is this plus C1. You need to have that plus C1 right there, otherwise it's going to be wrong, because remember, this is an arbitrary constant. Later on, we're going to solve for that. This is what we call an indefinite integral. It's considered indefinite because we don't know what C is, an indefinite integral. Indefinite again because we don't know that C value. So let's talk about trigs then. Well, we know that the derivative of sine is cosine. Now ignore this, they're just talking about some sort of chain rule right here. We'll talk about the chain rule for integrals later on. Okay, it's called U substitution. We'll talk about that. So if we're now looking for the antiderivative, I'm just going to go backwards, of cosine. So I draw my little integrand. The antiderivative of cosine of x, dx. Now remember, we want to have this dx right here because this is a derivative. In other words, this is a differential. We had that lesson yesterday, that dx says that this is a differential. So without the dx, it's going to be wrong. So if you forget your dx, it's going to be off. Well, what function's derivative is cosine? Well, we know that is sine. So this is just sine of x. Don't forget your c1. That c1 is also called the constant of integration. And on the AP, they give you a point just for having that. That's called the constant of integration. And that's because when you take its derivative, it just becomes 0. All right. Well, we know that the derivative of cosine is negative sine. So if we go backwards, if we take the antiderivative of sine of x dx, well, that's going to give us negative cosine of x plus c1. Now, I don't really remember the trig ones. I just remember what function's derivative that is. All right. So what about the, well, we know the derivative of tangent is secant squared. So the antiderivative of secant squared of x dx has to become tangent of x. Don't forget your plus c1. And we can just keep going. The antiderivative of cosecant of x. Well, the derivative of cotangent is negative cosecant. So the antiderivative of cosecant is going to be negative cotangent of x plus c1. All right. The derivative of secant, remember secant tangent, so the antiderivative of secant x, tangent of x, again, don't forget the dx, it's going to become secant of x plus c1. Now, be very careful. If you forget the dx and the c, you do lose a lot of points on these. Right, and then the derivative of cosecant is negative cosecant cotangent. So the antiderivative of cosecant x, cotangent of x dx, don't forget the dx, becomes negative cosecant of x plus c1. So a couple things to remember. One, this is what's called, this dx right here, this is the antiderivative right here, or the derivative part, sorry about that. This dx right here is called the differential, right? And this is our antiderivative right there. Okay, you need all of these parts for your answer. All right, and if you forget the dx, the AP will not give you credit for the antiderivative, setting up your integral. If you forget the plus c, they won't give you a point for your answer. So it's very important that we have these, okay? Now, I do have some good news and some bad news. Here's the good news. There is no, in antiderivatives, there is no product or quotient rule. Now there is, but we'll talk about that later on. It's not really a major thing. We don't think of it normally as product or quotient rule. But there is no product or quotient rule. Okay? And that's a big thing for us. All right. There is a chain rule. We will talk about that later on in a few days. Okay. Now, where do we get this information from? It's called how do we solve a differential. Now, we're going to talk about this later on. It's how we solve a differential. We solved this the other day, a differential the other day, and I'm just going to show you where all these parts come from. And this can become a really big topic for us later on. We know from experience that dy dx, which is the derivative, can be equal to f prime of x. We are going to solve for y. Well, if I want to solve for y, we know we have to get the x's to one side. So I can multiply both sides by dx. So we get f prime of x dx. This is our derivative part. Right over there, there's our derivative. And now when I solve it, because it's a derivative, I have to use antiderivatives. We have to use an antiderivative to solve this one. So remember, to solve this, we're now going to use an antiderivative. But before I begin that, what I want to point out is, remember this differential, that dx. Well, this is where it comes from. This dx comes from when we're trying to solve for the original function. When we solve a differential, a derivative, we're looking for that original function. This is like going from velocity to position. So that dx comes from our derivative, dy dx, and you see it right there. So when I integrate both sides, we get this dy and the integral of f prime of x dx. Well, we're going to talk about what this becomes later on, but I'm just going to tell you right now, this just becomes y. And remember what we said, the derivative and this antiderivative are inverses of each other. They cancel each other out. So if we're taking the integral of a derivative, we're going to get the original function back, f of x, plus this c1, this constant of integration. A little bit extra for your troubles right there. And this would be our function. Now this may not make too much sense right now, but it will over the next few days. Now one thing I want to point out again is that this is called an indefinite integral, and this is very important. And one thing that's very neat about this one is that of this function that we just found, this is not unique. And the reason why it's not unique is because we don't know c. You will see this question on the AP test, talking about uniqueness. All right, so go to part 2. We'll take a look at a bunch of examples here.